Hello everyone, this is me with another problem for you. Okay, so here is a problem with on rigid body equilibrium, of course, with a pin and a cable support. Okay, so let's look at this. So problem. Okay, in this problem I have some kind of a boxed structure, as you're going to be seeing in a minute. Okay, let me extend the size of this and let's make it looking good. Okay, all right, so here is the situation now. I have the following things going on in this problem. I have a pin support, okay, so which means that there is a small hole that was drilled in there, okay, and then through that hole there is a pin that is passing through, and then that is attached to the wall here. Okay, so this is an example of a pin support. Let me draw this as a straight line. And a common example of a pin support is your arm. Okay, you take your arm, you can rotate it about your shoulder cuff, your rotor cuff. And so similarly, pin supports are also the same. They allow you to rotate. I can take this entire body and I can start rotating it up and down, but I cannot move it horizontally or vertically. Okay, so this is an example of a pin support here. Okay, so let me draw the pin carefully as well. Okay, so this is a pin support. Okay, now you see that the problem is not in equilibrium, right? Because if I just let's say that there is another force acting on it. Let me say that there's a force acting on it. Okay, so let's say that this force here has a magnitude of 200 pounds. Okay, and then it is acting at an angle that is 60 degrees with respect to the horizontal. Okay, and let's say I have some dimensions for this problem as well. Okay, so halfway dimension for this problem is going to be 0.5 inches. Okay, so let me draw the dimensions out here, and we were going to draw these in terms of dotted lines, as you know. Okay, let me do that here as well. Bear with me for a second. And last one. Okay, and then these will be in the form of arrows. This is going to be 0.5 inches. Okay, and then this is also 0.5 inches, and I have one more dimension here from the top to the bottom. So the width of the beam is known to me, if you want to think of it that way. Okay, so these are also dimensions, so I'm going to mark them in the form of dotted lines. Okay, the angle is given to me, the angle made by the force is given to me as well as the height of this beam here. Okay, so this is going to be 1 inch. Okay, now you obviously see that this beam is not in equilibrium, right? Because I'm going to see that this force of 200 pounds has a component in the vertical direction, and that's going to start making the beam rotate. In statics, we don't want rotation. We don't want things to start moving and suddenly sprouting a life. Okay, we want things to be as they are. Okay, so here is what I'm going to do. I'm going to attach a cable. Okay, so this cable is going to be attached at this particular point. Okay, so there is a small pin that is put up here, and then this cable is attached here. Okay, so this is let me call this cable as A B. Okay, so this is a cable. Let me see. Okay, so I have a pin support, then I have a cable support, and obviously the question is, okay, find out all the reactions. Okay, so find all support reactions. Okay, so that's the name of the game, I guess. Once again, straight lines. Well, once again, straight lines. I don't know, something happens to me suddenly when I start drawing straight lines. Okay, so what am I going to do in this problem? I'm going to set up a coordinate frame. That is the first thing I do. Whether I know how to solve anything or not, I just draw a coordinate frame. Okay, that's almost like the ritual of brushing your teeth in the morning and in the night. You just do it whether you like it or not. Okay, then I draw a free body diagram of this structure. Okay, how do I do this? Is by taking this beam here, I'm just going to copy that guy, and then I'm going to just plop it down here. You see, when I'm drawing the free body diagram, I'm not drawing the pin, I'm not drawing the cable. I'm drawing only this box, and then on that I'm going to mark the effect of the cable and the effect of the pin and the other forces acting on it. Okay, so let's see, let's call this point as the point C. Okay, so let me say this is point C, and then I have the point A, and I guess that's good enough for me. Then what am I going to do? I'm going to mark the force that is acting. Okay, this 200-pound force. You see this 200-pound force, I can break it into its components, right? So I can break it into a component that is acting horizontally. Okay, and then I can break it into a component that is acting vertically. Okay, so this is going to be 200 cosine 60. This is going to be 200 sine 60. Okay, so I'm just going to mark those components right here. So I'm going to have one force acting this way, then I'm going to have another force acting this way. So this is going to be 200 sine 60, so many pounds, and this is going to be 200 cosine 60, so many pounds. Okay, then I have some dimensions and so on, so let me mark those dimensions very quickly. Okay, so I'm just going to copy my dimensions from here, because why not, right? I'm just going to copy that, and I'm going to paste that here. So dimensions are very, very important. Let me make sure that they are lined up all properly. Then I have one more dimension that I also want to copy from here. So let me take that and put that down here. Okay, fantastic. So I have all the dimensions done. Then I start thinking, okay, what does a cable do? Cables are always in tension. Okay, so here is the idea. If I take this cable and if I cut this cable off, okay, then the cable is, what is the cable trying to do? The cable is trying to prevent this ball or this bar from falling down, right? Which means that there is going to be a cable tension that is going to be pointed up. Okay, so look at this. I'm going to draw a bit of that cable. Okay, so essentially this is the place where I cut off that cable. Okay, which means that I'm going to see a cable reaction, which I'm going to call as tension T on the cable AB. Okay, so TAB is a cable reaction. So TAB is the cable reaction. Okay, cables are always in tension. Okay, which means that, if I, let's say for example, I have a cable from one point to the other. This is just drawing it hypothetically. This is not a real picture of any kind. Okay, so this is cable AB. Now the idea is this: if I cut the cable off here and if I cut the cable off here, right, if I draw these forces up, so there is one piece which I have here. Let me maybe draw it off here. So there is one piece here, then there's one piece in the middle, and then there's another piece here. Okay, and so if I look at the forces that arise from these pieces, cables are always in tension, so these two forces will be coming out this way. There will be a force here and there will be a force here, and of course this is the wall here, so there is going to be some reaction force. This is the cable tension. Okay, this is the cable tension. This is also the cable tension. So this is an example of how a cable is cut and the cable is in a state of tension. Okay, and this is exactly what we've done here. We have taken that cable off from here, we have cut it off so that the tension is pointing out that way. I hope this makes sense. Then I have the pin support. Okay, so I have the pin support which I had drawn here, right? But then I just see only the hole because I have removed the pin and I have removed the bar from all of that. Okay, so what am I going to do with that? Here is what I'm going to do. Look at a pin support. Okay, I'm going to draw the beam, but I'm not going to worry about the rest of the beam. I'm just going to look at only what is happening very close to the pin. Okay, so I don't worry about all the forces acting there. I'm looking only at what's happening near the pin. Okay, so here is the pin support. as you can see. What are all the things that you can do? Can you move this bar up and down? You cannot. Okay, that is not allowed because the pin prevents you from moving up and down. Can you move this bar horizontally? That is also not possible because the pin prevents you from taking this beam for a walk. Can I move it up and down? Can I rotate it? Because if you think of a pin, think of your arm. Can you take your arm for a walk? Can you detach your arm and then, let it go for a walk? You cannot, right? Because it prevents you from translating. The shoulder cuff, the rotor cuff prevents you from translating everywhere, but it allows you to rotate. Of course, it's a three-dimensional structure. So in 3D, this pin will be called as a ball and a socket joint, okay, which is an example of what your rotor cuff is. Okay, so it allows me to rotate, which means that a pin support prevents all translation but allows for rotation. Okay, so this is prevents. I just want to write it properly so that it looks like prevent. So prevents all translation but allows for rotation, which means that in 2D I'm going to have two reaction forces. I'm not going to have a reaction moment, okay? So which means that pin support only reaction forces for such a support. Okay. So which means I come back to my free body diagram. Once again, you see if I have a pin, I cannot move it horizontally. I cannot move it vertically, but I can think of this little piece here trying to rotate about that pin. If the pin is very rusty, I'm ignoring friction and so on, right? So there are some assumptions that I'm making here. I'm ignoring the weight and so on, but I'm still able to rotate it, okay? But I'm not able to translate it. Okay, so there are some assumptions that I'm making, which I want to probably list here very quickly. So assume weight is negligible, and friction is negligible, no friction at the pin. You don't want a creaky pin, okay? All right, so I come to this figure here and then I say, okay, at the point C, I'm just going to have some reaction forces. I don't know what these directions are going to be, but they're going to be my pin reactions, which I'm going to call as CX and CY, okay? So these are my pin reactions. This is my free body diagram. I'm going to copy it once again. I'm done with everything. I have the dimensions, I have the applied force, I have the support reactions. I'm going to copy it, and here I'm going to say that, okay, I'm going to have the pin reactions only CX and CY. And as we did in the previous problem, I'm just choosing them in some arbitrary direction, which is completely fine by me. Okay, I really don't care. I'm going to let the equations of equilibrium decide what the actual directions are going to be. Okay. Now I'm going to start summing up the forces, summing up the moments. There is no particular order in which I need to follow this summation procedure. Okay, so note, when using equations of equilibrium, we need not follow any particular order. That is, i.e., I can use the moment equation first, moment equilibrium first, and then use force equilibrium, or vice versa. Okay, there is no particular order in which I need to follow in the procedure. So what I'm going to do is I'm just going to start using the moment equation. Okay, so I'm just going to maybe scoot this statement down a little bit, okay, so that I can actually use the moment equation while looking at this figure here. So once again, when I'm using the equations of equilibrium, I don't need to follow any order. Who says that I have to do the summation of the forces first? I never said that. Newton did not tell that to me either, right? So you can choose to do what you want to do. And sometimes solving the moments first will actually give you something to solve for when you do the summation of the forces. Okay, so it might not be a bad idea. So in this problem, let me start off by summing moments. What's a good point to sum moments about? I typically like to sum moments about the point that has the maximum number of unknowns. Okay, so typically, I'm going to write down one more statement. I sum of moment at a point that contains the maximum number of unknowns. Okay, this is important, right? I mean, because then by doing so, I kind of knock out all those unknowns from the picture and I can find something else. Okay, so which means that I will be able to sum moments. So sum of moments at C, because that has the more number of unknowns here. Okay, so I'm going to sum moments about C. So let me write that down here. So summation of moments about the point C, I'm going to set that to 0. All the counterclockwise moments are going to be positive from now on. Please do not forget the 0. Please do not forget the counterclockwise sign. Start off by looking at the figure. Cx and Cy knocked out of the picture. TAB, right hand rule. What is the distance? I guess the point C, if you are really particular about it, you can move them right down here, so that this is the point C, and maybe let me redraw this again. Okay, I guess I should have done it this way. Okay, that's better. Okay, so here is the point C. Okay, if you want to think of it that way. You can also think of the point C as being here, and then this distance is very inconsequential or very small, so because it's not given to me in the problem, right? What am I going to do about it? Okay, so I'm going to just say the point C is right there. Then I say, okay, what is the perpendicular distance from the line of action of TAB to the point C? Okay, this is fairly obvious here, right? Because if I extend this distance here, and if I extend the line of action, I see that the distance for that is 0.5 inches. And what is the direction of the moment? Right hand rule, TAB, fingers aligned to TAB, my palm faces the point C, curl your fingers counterclockwise. Okay, so this is going to be TAB times 0.5. Then I come to the other two forces here, 200 cosine 60 all the way to the point right there, which is point C. What is that going to be? What is the perpendicular distance? Now you got to be a little careful. Okay, so you got to be a little careful. Here is the situation. So from point C, I draw a line that is parallel to the line of action of the 200 cosine 60 pound force, and I see, okay, hey, the perpendicular distance is going to be a distance of 0.5 inches once again. Okay, and then what is the direction of the moment? Right hand rule says that if I align fingers of my right hand with the 200 cosine 60, my palm faces the point C, curl your fingers, it's going to be counterclockwise. Okay, make sure you understand why this is counterclockwise. So this is 200 times cosine 60 times the distance of 0.5, counterclockwise. Right hand rule, once again, fingers of your right hand with the force 200 cosine 60, your palm faces the point C, curl your fingers, points up, thumb points up, so the sense is counterclockwise. Last one, 200 sine 60, what is the perpendicular distance? It's fairly straightforward to see that that distance is going to be a distance of 1 inch, 0.5 plus 0.5, right? Because this distance is also 0.5 here, and so the total distance to the point C is 1 inch. Right hand rule tells me that this is going to be a clockwise moment. Fingers of my right hand with the force 200 sine 60, palm faces the point C, curl your fingers into the page. Okay, so this is going to be minus 200 sine 60 times 1, all of them set to 0. I can solve for the tension. TAB is the unknown here. Okay, so which means that TAB is going to end up being around 246.4 pounds. Okay, so note, tension always has to give a positive answer. Okay, this is not something that you choose. So which means that when you're marking tension, on the free body diagram, do not choose arbitrary direction. Okay, this is true only for the tension. For any other support reaction, you can choose arbitrary direction. Okay, so for any other support reaction, we can choose arbitrary direction. But not for the tension, because we know that cables are in a state of tension. So if I end up getting a negative tension, it makes no sense. I mean, you know that the cable is in a state of tension, so the way you draw the force is also such that the cable is in a state of tension. Okay, so tension always has to give you a positive answer, and this is exactly what it has given us here. Then I go ahead and I say, okay, now I'm going to start summing forces up in the x and the y directions. Okay, so maybe I want to take my figure once again and bring it down so that I start summing up my forces. Okay, so I'm going to bring it down here. And what are the forces in the x direction and the y direction? So sum of all the forces in the x direction, all the forces pointing to the right are positive. This is going to give me minus cx minus 200 cosine 60. Okay, which tells me that cx is equal to minus 100 pounds, which is okay because I did not know the direction of cx to begin with. I mean, even though I knew, I just acted as if I did not know. But this is completely fine. Sum of all the forces in the y direction is equal to 0. I have cy. TAB is pointing up. And then I have this force of minus 200 sine 60, which is pointing down. All of them have to be set to 0. Okay, I made a small mistake here. This has to all be set to 0 here. Apologies for that. This is equal to 0. And so this implies cy is 200 sine 60 minus TAB, but we know TAB is 246.4 pounds, which tells me that cy, after solving, cy is going to be minus 73.1 pounds. Note this very nice thing here. If I did not solve for TAB first, I would not have been able to solve for cy. Okay, so if I had started the problem with the force equations, then we would not know what TAB was. Okay, which is why I started with the moment balance. But then you're going to ask me, hey, how do you know what to start with? And my answer is, we don't know what to start with. So in many situations, you may have to solve all the three equations and then find out all the unknowns from that. Okay, so in most situations, we do not know what equation to start with. That is force equilibrium or moment equilibrium. and it is okay. It is okay to start with something and then eventually solve for all the unknowns. Okay, and then eventually solve for all the unknowns. Okay, so sometimes, which means that you may end up having to solve a system of equations. Okay, so this means that sometimes we may end up having to solve a system of equations. Which is completely fine, because I don't know whether to start with force or a moment equilibrium. Who tells me? Nobody tells me, right? So I just choose something that I feel comfortable with. If you're comfortable with force equilibrium, start with that. If you end up with an unknown, then you need to go and do the moment equilibrium. But always remember, in a two-dimensional problem, you are going to have only three equations, which means the maximum number of unknowns that you can have in any problem is only three. And that's the case in our situation as well, right? When we started the problem, this was an unknown, cx was an unknown, cy was an unknown, tab was an unknown. So only three unknowns, but then I have three equations of equilibrium, which will allow me to find out all of these unknowns here, and then tab was found out by using the moment balance equation. Okay, very quick recap. Here is the problem. I have a pin support, I have a cable support, I have some force applied. Find the support reactions. Cables are always in tension. Always remember, cables in statics are always in tension, which means that when I draw the reaction support free body diagram, the cable tension always has to point away from the cut. Okay, so this points away from the cut. Notice that this cable tension points away from the cut. That's one way of remembering what is the proper direction for tension. Then I say, okay, here I have a pin reaction here. What am I going to do with that? I come here and think, okay, what does a pin do? Or what does a pin not do? A pin prevents me from translating horizontally, prevents me from translating vertically, but it allows me to rotate, which means I don't have any reaction moments. I have only reaction forces, because there is no resistance to rotation, right? So since no resistance to rotation, no reaction moment. You see, it is as simple as that. But there is some resistance to translation, right? The pin does not let me move horizontally or vertically, which means I'm going to have support reactions in those directions, and that's exactly what I have here in the form of cx and cy. Okay, and then I come back and say, okay, I have all these unknowns here, cx, cy, and then tab, three unknowns, three equations. I start using the equations of equilibrium. What do I start with? I don't know. In this problem, I just made a bet and I said, okay, let me start with the moment balance or the moment equilibrium. When you do the moment equation, always choose a point, typically, not always, but typically, choose a point that has the maximum number of unknowns. Okay, so in that situation, the point C has the maximum number of unknowns, and so that's why I choose the point C. Okay, and even here, these forces, you can kind of shift them out if you want. Okay, so this is I guess not the best way of looking at it, but okay, that did not work out. Okay, so maybe here is what I needed to do. All right, I got it. All right. I just wanted to move it such that that, because the dimension, as you can see here, I was not told what this dimension is. Okay, so I'm not given the dimension, so that is negligible. So this is negligible. So which is why I just moved everything down there. Okay, all right. So then I start by summing moments at the point C, and then I end up with the solution for the tension. The tension is always going to be a positive value. Okay, this is something that I'm very particular about. If you get a negative value, even though your magnitude is correct, you will not receive any score for that. You will not receive any credit for that. Okay, and then I find the other support reactions by summing forces up in the x and the y directions. Okay, and so the question is, what do I start the problem with? I don't know. Sometimes I may not have any idea on which equation to start off with, so I use all the equations, and then I might end up having to solve a system of equations, which is completely fine. All right, so this is an excellent problem. Once again, a fairly gentle problem. We're going to solve a little more complicated one later on, okay? But I hope this is a good introduction to rigid body equilibrium. Thank you very much, and all of you stay safe. Bye bye.